Yeah, hello and welcome to my talk. First, let me thank the organizers, Elio and Thomas, for the very nice invitation. I actually feel very honored and privileged to be part of this wonderful workshop. As you can see from the title here, my presentation is going to illustrate that there are graphene moiré systems other than the famous twisted bilayer graphene that also show very interesting, strongly correlated many-body physics, and in fact have also been realized experimentally quite recently. Nonetheless, I thought just to set up the nomenclature and also to connect to Erisberg's wonderful introduction yesterday, I like to start with a few words on twisted bilayer graphene. So in this case, we have two layers of graphene, which we twist relative to each other and put one on top of the other, which creates this famous moiré pattern of carbon atoms. And at least in the limit of small twist angles, theta, we have approximate translation symmetry, which means that we can Fourier transform and even talk about a band structure. The band structure can actually be intuitively understood if we first look at the limit of decoupled layers. So you see here the brown zone of, say, the red layer. Here is the brown zone of the blue layer. And if you work out the details, you will notice that the moiré brown zone is geometrically related to those two in this way. And so we can immediately conclude that there will be two Dirac cones associated with valley plus from the individual graphene layers at k and k prime of the moiré brown zone. And in fact, things are periodic in momentum space, and so we will have two additional Dirac cones associated with valley minus of the individual layers. Now, in the actual system, there's an interlayer coupling, but it turns out for the small angles where we will have a couple of thousand small hexagons in the big hexagon, the momentum transfer from here to here is very large in the scale of the small hexagon. And for that reason, valley will remain a good quantum number, also in the coupled system. And in fact, this holds true for all of the systems I'm going to discuss today. So compared to single layer graphene, on top of the two spin degrees of freedom, the two valleys, the two bands that form the Dirac cones, we also have the two valley degrees of freedom. Now, the band structure can be conveniently computed in certain continuum model approximations. So here you see such a result of such a calculation. And in particular, we see that the Dirac cones actually survive the interlayer coupling, and this can be traced back to the presence of a C to Z symmetry, twofold rotation combined with time reversal. Now here you can see the evolution of the band structure when decreasing the twist angle, and you see the brown zone becomes smaller and the bands become increasingly flat, which is maybe not that surprising. But what is in fact quite magical, if you will, is that something happens at a 1.1 degree where the bands almost become perfectly flat, and hence it's natural to expect that in this regime, correlations are enhanced, is in fact seen experimentally. But as I anticipated, I would like to talk about different graphene moiré systems. And the first one I would like to mention is twisted double bilayer graphene. So in this case, we start with AB stack bilayer graphene, take two copies of that. I twist those two relative to each other and put the other on top of one on top of the other, which creates this even more complicated moiré superlattice. Now you might think, why would I ever want to study such a complicated moiré superlattice? Well, one added benefit is that the system is very susceptible to and hence can be tuned by the application of a perpendicular electric field, which is also often referred to as displacement field, and I will denote it by D0 in this talk. And the system has been realized experimentally, and this gate tunability, this displacement field tunability has been observed, and even in this first set of experiments, already signs of strongly correlated behavior, such as correlated insulators, and possibly superconductivity have been observed. If I have some time at the end, I will come back to twisted double bilayer graphene and provide briefly some evidence for nematic order, discuss its predominant microscopic nature, and I will further illustrate using nematicity the displacement field tunability of the physics of that system. But the main focus for my talk today will be on yet another system, which is even more recent, which is mirror-symmetric twisted tri-layer graphene. Okay, so as the name suggests, we have three layers of graphene. The top and the bottom one, they're aligned. And in between, there's one that is twisted relative to the other two. And as you can see from the title here, it does have a mirror symmetry. Exchanging these two layers leaves the band structure, the system invariant. And this has some consequences for the eigenstates of the system, including the non-interacting bands, which can be labeled by the mirror symmetry eigenvalues. And it turns out that the mirror even bands are equivalent to those of twisted bilayer graphene modulo some rescaling of the parameters. For instance, you see again these flat bands indicated here in red, and the mirror odd sector is equivalent to that of single layer graphene, as you can see in this highly dispersive Dirac cones here. Now, if you apply a displacement field, you break the symmetry, and hence you will mix these bands, right? Then, for instance, here you can see the band structure once a finite displacement field is applied. Now, this system has also been realized experimentally very recently, as reported in these two papers that came out just a few months ago. And I mean, there's a lot to discuss concerning experiments, but I will be brief here and just flash some schematic summary taken from Pablo's paper, this paper right here, where you can see where you have two axes. One is the electron concentration, noted here as filling fraction, and here again the displacement field. And there are several lines, and let me just mention a few. So here in red, you can see the positions here in the phase diagram where they see signs which could either come from the Dirac cone or from a gap. And there are also signs of what is referred in this community as resetting, which means that if you tune through this point here, the system will spontaneously, probably due to interactions, reduce the number of active flavors in the band structure. I will come back to this resetting later if that doesn't make too much sense to you at this point. And I'd like to emphasize further that they've seen superconductivity in these blue regions. And in fact, as reported in this even more recent paper, they see that some of these superconducting domes can survive very large in-plane magnetic fields up to about 10 Tesla, which is a couple of times larger than at least naive estimates for the polynomial. And what I would like to discuss here is a recent attempt to understand some of the correlated normal state behavior in this system, particularly correlated insulators or semi-metals, as well as this resetting, and then use these insights to make a few statements about possible origins of superconductivity and order parameters. Okay, so this is going to be the topic of the first and main part of this talk. And sort of in the tradition of a theory talk, I'd like to start this discussion with specifying my Hamiltonian. So the Hamiltonian has two parts. One is just the non-interacting part, which just captures the band structure. So for our analytics, more specifically, we keep this almost flat band, as well as these dispersive Dirac cones. For the numerics, we also take into account a couple of those remote bands, but just for the aspects I will mention here in this talk, you can just forget about the remote bands. Now, the interacting part, we use the gate screen Coulomb interaction. So rho here are the density operators projected onto those low energy degrees of freedom that we keep in the calculation. So here F are, the electronic field operators F and F dagger, which are vectors in band, spin, and valley space. And capital F are form factors, which are matrices in the same space, and they contain matrix elements of the Bloch functions here. And this is just some offset that is required for technical reasons in the projection that makes sure that we don't lose some essential symmetries. Now, the first point I would like to make is that these form factors are diagonal in spin space, well, simply because we don't have spin orbit coupling. And they will also be diagonal in valley space because, as I mentioned before, valley is a good quantum number of the non-interacting bands. And this leads to this enhanced SU2 cross SU2 spin symmetry, which simply means you can independently rotate the spin in valley plus and valley minus. Now, to get started with the interacting physics, I think it's a good idea to start with the simplest and yet non-trivial limit possible, which is the following one. So let's assume we take the TBG bands to be perfectly flat. So only those, the Dirac cones, will remain dispersive. We focus on displacement field 0, which simply means that the bands decouple into mirror symmetry eigenvalues. And we further take the tunneling matrix elements between the layers between like sublattices to be 0. And for the experts, it means that we have some chirosymmetry in that model. Now, schematically, the Hamiltonian now has this structure. There's a part describing the graphene part with some interaction. There's a TBG Hamiltonian with interactions, and there's a coupling between the two. And the first thing one can show is that in this simple limit, the ground states of this Hamiltonian at integer filling will also be eigenstates of this full Hamiltonian, which is a consequence of some sort of funky properties of the ground states of this Hamiltonian in this specific limit. And one can also argue that they will remain ground states in a finite range of this lambda, which I just introduced here by hand to adiabatically turn on the interaction. And I think at the very least, this tells us that a good starting point for our analysis will be the eigenstates of this Hamiltonian. Now, luckily, we understand graphene quite well. So we know that it's a semi-metal, and TPG, of course, there's a lot of debate and a big open question, and there's talked about this yesterday with a lot of progress is now being made in numerics. But since we're here in this simple limit, in fact, we know quite well based on various publications. I just put a few here. I hope I didn't offend anyone, but based on various publications, we now understand that there's an entire manifold of exactly degenerate ground states in this simple limit of the TBG Hamiltonian. And so in order to construct realistic candidate states for this full system, what we did is just take this manifold of states and pick the single, a finite number of discrete points on this manifold, finite number of states, which transform under the irreducible representation of the symmetries of the actual Hamiltonian that we studied. Okay, and this gives rise to this finite and discrete set of candidate orders. So I don't want to overwhelm you. Let me just walk you through one line in this table. Okay. So for instance, one state is just a spin polarized state. That's probably the simplest state you can think of. So the order parameter is a triplet under spin rotation. The valley conservation is not broken. Valley U1 is still symmetry. C2Z is preserved, and it's odd under spin photon reversal. Now, as I said, this model has an enhanced spin symmetry, this SU2 plus SU2 symmetry. And this means that the spin polarized state will be exactly degenerate with another state, which you can think of as a spin valley locked or spin valley polarized state. And the point is that in a realistic system, there will be some inter-valley Hund's coupling, which will favor this one or that one. And we call these two pairs of states Hund's partners because when you change the sign of this Hund's coupling, one of them will transition into the other. Okay. There are other types of states similar to states that have been discussed in the TBG. Of course, the inter-valley coherent state, which simply means that one valley is broken and there certain, you might think of them as sublattice polarized states, which break C to Z theta, and of course will gap out the Dirac cones because they break that symmetry. And you can also think of them as quantum Hall, quantum valley Hall, or quantum spin Hall versions of states from graphene. Now, as I said, we have this enhanced spin symmetry, and always pairs of states will be exactly degenerate in the Hamiltonian we study energetics in. And for that reason, we can actually focus on only one member of these different Hund's pairs of states. And at the end, I will come back to what the actual, microscopic realization will be for the two possible signs of this coupling. So to study the relative energetics of those states, we did two things, which I think complement each other and yield at the end a quite consistent picture. We use both analytical perturbation theory as well as, unconstrained self-consistent Hartree-Fock numerics. So the advantage of the analytical perturbation theory can, loosely speaking, think of as starting at this fine-tuned point and taking the TBG bandwidth, W0 and D0 as perturbations. And the advantage of that is that it actually gives you some intuition for what the different contributions are to the energetics and structure of the states. So for instance, you will see that the deformations of form factors of the interaction matrix elements that factor in. There can be additional ordering happening in the graphene bands, right? That gaps out the Dirac cones. There can be mixing between the two systems, and there will be also super exchange processes, if you want to think about it that way, or put differently, second order perturbation theory simply in the finite bandwidth of the TBG bands. And the Hartree-Fock is just motivated because it's a very new system, so it's a very natural starting point, and also by the fact that this eigenstates in this fine-tuned limit are actually product states, so it can connect to this fine-tuned limit. And furthermore, it's motivated by at least the popularity, but I would even go as far as say the partial success of Hartree-Fock in some of the studies of twisted bilayer graphene, where, for instance, one has seen a good agreement with VMRG where almost product states were found. And of course, I don't have time to discuss all of this in detail. I would just flash a few results. So maybe let's start at the charge neutrality point. And here, let's draw a theorist space diagram. So this is the W0s, again, this intra-sublattice tunneling matrix element. Previously, we focused on W0 being 0, and D0 is the displacement. And there's this green region here where we find some inter-valley coherent states. So here you can see the band structure. This is again without any order, and you see that what this ordering does, it does gap out some of the Dirac cones. It will push out, some of those bands, but these Dirac cones in this limit will survive, and in fact, they will also survive at finite displacement field for a while because they are protected by symmetry in that state. And we also, and one comment I wanted to make is that at least based on my understanding of the experiment, this state will be consistent with the Landau-Fan sequence seen around charge neutrality in Philip Kim's data. Now, subleading instability here would be a spin polarized state or valley polarized state. If you increase D0, then you will see that eventually the subleading instability will be some quantum spin Hall state, which eventually becomes the leading instability. And what it does, it does gap out the Dirac cones, all of them. And you can get from the analytics some intuition for why this happens. So there are actually two contributions. So first of all, the displacement field induced changes in the interaction matrix elements will suppress the intervalley coherent state with respect to the quantum spin Hall. And also the quantum spin Hall is some unique state that can actually very efficiently benefit from the displacement field induced super exchange processes due to the mixing between the two subsystems. Okay, so from this, based on this theoretical phase diagram, we can maybe try to draw a more experimentally relevant, but at the same time more schematic phase diagram. So here, one axis is displacement field, the other one is the electron density. And so we discussed before at nu equals 0, seems to be some intervalley coherent semi-metal that is favored in this analysis and eventually turns into an insulating state. But we also looked at nu equals 2. And here the energetics turns out to be quite similar. But on top of that, we get additional spin polarization. So what that means is, for instance, for this IVC state, so say one spin flavor will have this intervalley coherent order, and one additional spin flavor will be just entirely be populated for nu equals 2 and pushed below the Fermi level. And this could be a potential explanation of the flavor polarization, this resetting behavior that I mentioned earlier in experiment. So schematically, you can think we can indicate this here. So at nu equals 2, we first have this IVC and eventually quantum spin Hall state. And here I extended the spin polarized region just motivated by experiment to finite values of nu away from nu equals 2, although technically we haven't studied this yet, but just to arrive at a final schematic phase diagram at the end, I will draw it this way. But to complete this phase diagram, we have to talk about superconductivity, right? And in order to do that, I thought it's maybe a good idea to go one step back and reconsider a project I did with a graduate student about 1.5 years ago. And we're just generally asking the question, how many and what different types of possible superconducting phase diagrams existed quite generally in these graphene moiré systems in the vicinity of these high symmetry points. Okay, so I'm interested in schematic phase diagrams where one axis is temperature and another axis is denoted by delta here. And you can think of this delta as some effective low energy interaction in the Cooper channel that sort of is similar to the intervalley Hund's coupling. And if delta is 0, we have this SU2 plus SU2 symmetry, which in fact is isomorphic to SO4, and it rotates a 4-component vector, in this case consisting of the singlet, one singlet component and the 3 triplet component. And that's the reason why these two have to be degenerate and have to meet at this point, the two states. But if you go at non-zero delta, you will either have singlet or triplet. Now, in general, the question of what different types of phase diagrams of that sort exist is very complicated, and we classified all options, which is very rich. But in the interest of this talk, I would like just to focus on the simplest option, which is pairing in the trivial representation of the point group. And in that case, there are only 2 possible phase diagrams associated with the unitary triplet or the non-unitary triplet. Now, the question is, of course, what happens at lower temperatures, right? Is it possible to have like 2 consecutive transitions such that we obtain a mixed phase? And luckily, the answer is entirely determined by symmetry. And one finds that for the unitary triplet, its state on the other side, which is again the Hund's partner of that state, is just always going to be a non-at mixed singlet, whereas in the case of a non-unitary triplet, we generally get a singlet triplet at mixed phase as the Hund's partner. And I think it's actually at least a quite interesting observation that we can get singlet triplet at mixture in such a system, because if you compare with the conventional mechanism based on spin-orbit coupling, which breaks spin rotation symmetry and hence is based on the reduced symmetry, it here happens in the absence of spin-orbit coupling and results from the proximity to an enhanced symmetry. So this is the symmetry discussion, and we also looked a little bit into generic energetics. So if you compare these 2 options, you can see that any low energy mean field theory will always favor phase diagram A over B, just because it optimizes the gap structure. But if you consider fluctuation corrections to this quadratic term in the Ginzburg-Landau expansion, you actually can show that if these are sufficiently strong, you can favor phase diagram B over phase diagram A.
Mathias,
okay.
You have 5 minutes left of talking time.
Yeah, that's fine. That's fine. Now, with this information, we can come back to the phase diagram of twisted trilayer graphene. And first discuss, I should first discuss some possible pictorial model for pairing here. And for this, I would like to go back to something we proposed in the context of a slightly different graphene moiré system. But I think it's actually quite natural also in this case. And the picture is the following. So, maybe electron-phonon coupling is really important to stabilize superconductivity. It's actually supported by experiments that show once you screen the Coulomb interaction quite strongly, superconductivity can still survive. But it might just be the case that the electron-phonon coupling predominantly mediates an interaction in this SU2 cross SU2 symmetric channel. And ultimately, some additional interactions decide, where the singlet, triplet, also a mixture of the two wins, or in other words, what the sign of delta is in the schematic phase diagrams. And you can analyze this for tri-layer graphene here. So let's maybe start with the superconducting region right here. And let's first focus on the Hund's coupling being negative, which means that the spins want to be aligned in the two valleys, ferromagnetic. And that's the sign you get by just naively projecting the Coulomb interaction. And in that case, this is just both valleys have the same orientation of the spin, and hence the superconductor you get by fluctuation corrections here will be a triplet state. If you do the same thing around mu equals 0 for the same sign of J Hund's, you actually obtain a singlet. Now, there are some indications that possibly superconductivity coexists with this polarized space. And in this case, the state you get here is a non-unitary triplet. Now, of course, we ultimately don't quite know the sign of J Hund's. And that's why we also study the opposite sign, which might be antiferromagnetic, right? In the two valleys, might come from phonons or maybe some strong renormalization of the Coulomb interaction. And in that case, this will be a singlet triplet at mixed phase. Here you get either a singlet or a singlet triplet at mixed phase, and this will be a triplet state. And just two quick comments maybe on this. First of all, I think both options here for superconductivity in this regime 3 are consistent with the dilation of the Pauli limit. And I also would like to point out that, as we discussed in some paper previously, that if indeed some triplet state is realized here in the vicinity of this point, it might be important to notice that it has at least some partial protection from some Anderson theorem, despite being a triplet, because it's protected against non-magnetic impurities that are smooth on the atomic scale. And if I have maybe 3 minutes left or so, I can just make a few comments on, twisted double bilayer graphene. Let me just briefly talk about some key insight coming from an experimental collaboration that I was very fortunate to be involved in with the group of Abhay Pasupati, where twisted double bilayer graphene samples, topography scan is shown here, were studied with STM. And just the main feature of the data is the following. So here, let's take a look at the energy-dependent local density of states. Here, first the charge neutrality. And here, this is shown at different energies. And you can see that across these energies, the data is roughly C3 symmetric. Now let's change the chemical potential to be located in the middle of the conduction band. So we dope the system with electrons, and you see that at energies corresponding to this valence band, here you get very strong indications of stripes, which indicate that you have a doping-dependent spontaneous breaking of rotational symmetry. So that might be an indication of electronic nematic order in the system. And a question that is important as theorists to ask is, what is the microscopic form of this nematic order? And of course, it's clear it's a two-component nematic director. That's obvious by symmetry. But the question is, how does this object couple microscopically to the electronic operators in the system? And another way to say that, what is this coupling function here? And there's so many degrees of freedom, right? Because we have so many atoms per unit cell. There are sublattices. There are 4 different layers, and there are 2 values. And of course, extracting this directly from the data is complicated, but what we did is we looked at several natural limiting cases, out of which I would like to briefly mention 2, and compared with experiment. And what we consider is, first of all, there's what we call moiré nematic. It's a state that is entirely trivial in these internal indices, and its nematic structure comes just from this R dependence, which you can restrict to nearest neighbors. And you can just think of it as a distortion of the bonds on the scale of the moiré lattice. And the other limit is the graphene nematic, where everything happens in the sublattice indices. And you can think of this as a distortion on the microscopic scale of the graphene bonds. And comparison with data shows that while the moiré nematic is consistent, the graphene nematic is not. And so at least the predominant nature of nematicity is more likely to be of this moiré nematic form. And just 1 minute, if that's all right, I just make a brief comment on gauge tunability, just theoretically on of the nematic director. So if you don't have a displacement field, we have C3 and C2x symmetry. And if you look at the nematic director in this complex notation and work out how the symmetries act, you can write on the free energy, and you can minimize it, and there are just 2 discrete set of orientations. Now you apply displacement field, so you break the symmetry. A new term is possible, which depends on the displacement field, and this term now allows to rotate the orientation of the nematic director just by applying electric field in the system. Of course, the question is how large this is, and we investigated this microscopically, and you see actually that there's a quite sizable rotation possible within experimental reach. And while SDM might not be the best way to detect it, we propose transport measurements which can actually directly access the nematic director orientation, in particular its change. But I'm not going to go over this in detail, and instead just flash my conclusion slide. So in the first part of the talk, I discussed twisted trilayer graphene, a very new system, and we discussed normal state properties and superconducting tendencies. And of course, this is just the starting point. I mean, very new. This is our first attempt to understand the system. And in particular, given the nature of this conference, I would be excited to hear about ideas of how to apply more elaborate numerical techniques on this. Maybe we can talk about this over some coffee break or so. And then we discussed twisted double wire layer graphene, nematic order, and gate and displacement field tunability. And at this point, it's only left for me to thank my collaborators here for the projects related to twisted trilayer graphene section, and here twisted double wire layer graphene, and you for your attention.